Now let's move to the second application. I mean, the general application is same, that is you are finding the electric field, but now we are finding electric field due to another source of charge, right? So here, what is the charged conductor here, or the charged material? We have already seen the linear distribution of charge. So now let's say we have let's say the charge source here is a sheet of charge like this. Let's say this is the sheet of charge. So here it is surface distribution of charge. Let's say that is sigma, and it has all, let's say, positive charges here. Uniformly charged, right? So this is uniform charge distribution here. Now, due to this, you may have to find electric field at a particular point. So let's say we have to find the electric field at this point. So what we are going to do is, here we will again try to think of a Gaussian surface. That is the first thing which we have to do. So what should be the Gaussian surface here? So again, you can, and this is an infinitely long, thin, plane sheet of charge. So the length is infinite, width is infinite. It is long, thin plate. Thin means on the left hand side also you see the positive charge, on right hand side, that is from this side, if you see there also you will be seeing the positive charges. So now here, if you have to find electric field, you have to think of a Gaussian surface, and the Gaussian surface which comes into my mind is a cylindrical surface again, because again I cannot take it as a sphere for the same reason which we have seen earlier. So let's say this is the point on the surface, and here you have to find the electric field. So think let's imagine surface this surface is what? It is a spherical surface. So this surface will be on both the sides, right? So that's what this is, the surface. Let's say this distance or the radius of this cylindrical surface is r, right? Now, what about the electric fields here? We already know that electric field on these ends will be like this, because the positive charge is here, and that's why if you take this point, the electric field will be in the direction which I have already shown. At this point, let's say this surface is surface A, this flat surface is surface B, and the curved surface is surface C. So at A and B, you can see the E and ds will be in the same direction on the flat surfaces. So E and ds are in the same direction. It is just opposite of what we have seen earlier. In earlier case, E and ds were perpendicular at the flat surfaces, right? And that case will be actually here. So suppose if this is ds, you can see that ds will be like this, and we already know that at this point or at any point the electric field is going to be in this direction. So the angle between electric field and ds is 90 degree here. So from the previous example, you must be clear by now that electric field due to this will be equal to, I mean, E dot ds will be 0, not electric field. E dot ds will be 0. Okay, so that was our surface. Now let's find out, or let's proceed. You have to find the total surface integral of this electric field, which I can divide it into 3, that is along A, B, and C, right? So you can see I have divided this closed integral into three integrals where the surface area is or the surface is not closed. So that's why I'm not drawing this ring in the integration sign on the right hand side. So this is also E dot ds. This is third one is also integration of E dot ds. But in the third case, that is along C, we know that this is equals to 0 because cos 90 degree is 0. And in these two cases, you have EDS, EDS. So basically both are same, 2 into E into integration of ds for surface A or B. So this is the flux. That is our calculation. Now what about the charge enclosed? So total charge enclosed will be equal to what? It will be equal to the surface area, that is pi r square, into sigma, which is the surface charge density. Sigma is total charge divided by area. Area is pi r square. So charge enclosed is pi r square into sigma. Done. And now, okay, here we have missed, we have not completed this integration. This integration is ds has to be integrated, and ds is a small area on this surface, so total area will be equal to what? It will be pi r square, that is the area of the circle. So this is 2e into pi r square. So this 2 into pi r square and this q, they are related. That is nothing but your Gauss theorem. How are they related? The total flux, that is 2e pi r square, should be equal to charge enclosed, that is pi r square into sigma divided by epsilon naught. So this pi r square and pi r square gets cancelled, and you have the final expression of electric field due to a surface charge. So that is equals to that is E is equals to sigma divided by 2 into epsilon naught. Actually, just 1 minute. Yeah, E is sigma divided by, sorry, sigma divided by 2 epsilon naught. That is the electric field near a charge, near a surface charge distribution. And if you see the previous, right, in the previous one also you had a similar expression for the long wire, that was E is equals to lambda divided by 2 pi r into epsilon naught. So there is epsilon naught in the denominator in both the cases, but the for linear charge, the distance from the charge matters, while there is no such thing here in this case, in case of surface charge density or surface charge distribution. Okay, so that is about the electric field due to a surface charge. Now there is a variation here, and that variation is what if there is a thick surface? So if there is a thick surface, that means now you won't be able to, thin surface means what? There is only one charge, plus charge, which was visible on both the sides. But now this thick surface means it is a thick surface like this. And due to this thickness, charge here and charge here are two different things. These are two different sheets, right? So if you are finding electric field here, there will be electric field here due to surface A as well as surface B, or due to charge distribution on surface A as well as surface B. So if it is a thick surface uniformly charged, that means there will be sigma into area and sigma into the area on both the surfaces. So that will be the total charge. So that means the total charge will be doubled, and that means the above expression will be what? 2e pi r square. That is this 2e pi r square, which is flux, that should be equal to total charge enclosed, which will be twice of the above. So this will be twice of the total charge enclosed will change if it is a thick surface. it will be twice of this. So this will be the expression, and if you simplify it, you will get that electric field is sigma divided by epsilon naught. And if you see, if you compare these two, what do you think? So if this is a thin surface, it is only due to one surface, and that's why that is half of the electric field in case of thick surface. So that is the difference. Okay, that is about the plane sheet, infinitely long and wide, thin plane sheet, and even the thick version we have seen. And we have seen that it is independent of the distance from the sheet. So that means electric field will remain same wherever you go, if it is infinitely long sheet of charge. Okay, so that was about this. In next session or in next video, I'll explain you few more applications.